Imagine you're moving. So you pack all of your things into this big moving truck and you drive it off to your new home. Now, before you can finish, you have to get your refrigerator into the truck. So it's down here and you need it up here. In order to move it up this change in height, you have to increase its gravitational potential energy. But to increase its energy requires work from you. And the work that you do raises it to this greater height. There's an equation, though, for work. Work is force times distance. There is also the cosine of the angle between the force and displacement. But we assume that you push, your force, we assume, is in the direction of the distance. And that means cosine of 0 is all 1. Now, if you come up and bear hug this thing, and you try to just lift straight up, you have no hope, right? There's no possible way because it's far too heavy. The gravity force is huge. So what do you do instead? To do this work, to achieve this increase in energy, you have to use a simple machine. The machine that we're going to use in this case is called an inclined plane, and you've seen it before. You put this thing on its side, and now all of a sudden, it's way easier to push up. Why is that? Well, there is still this giant gravity force. But here's where the machine comes in handy. The ramp, the inclined plane, exerts a huge normal force. And that huge normal force cancels out most of gravity. These two parts cancel. And all you're left with is this tiny little component of the gravity force. So when you try to go push this thing up, all you have to push is hard enough to overcome the small component. That's why machines are so awesome. They reduce the force. But check it out. If you want to get the same work done, if you want to move it all the way to the top, you'll have to push over a bigger distance. And that makes sense, right? You start over here and you have to push across this entire distance, whereas if you lifted straight up, that'd be much less distance. But that's okay. We prefer this. Machines are still useful. So we take the trade-off between force and distance. Now, that's one thing machines do. They reduce the force needed in order to get the work done. But you can see they also redirect the force, which is useful because if you try to pull straight up, you'll hurt your back. But it's actually a little bit worse than this. Real machines have friction. And so when you push up the ramp like this, you have another force to overcome. There's also this friction force pushing down, and so your force must be a little bit stronger. You've actually got to do more work to get it all the way up. So what does that mean? Machines are not perfectly efficient. Here's the machine. You have to do work, some input work, in order to make the machine work or make it, use the machine. And as a result, you get out some useful output. Now, in most cases, the useful output is the increase in potential energy. If you're using a pulley, like this, and you're raising some heavy thing as you pull, the output, again, is that you're raising this block, increasing its potential energy. Same goes for an inclined plane. As it goes up, you increase its potential energy. But you have to put in work, you have to pull, you have to exert some force, and because they have friction, real machines, your work that you put in is bigger. So if you put in like 200 joules, and let's say you only get out, how about 150 joules, then we could measure the efficiency. This is the Greek letter eta. How good is this machine, efficiency, by taking the input work, taking the output work, what you get out, the useful output, and dividing by the input work. In this case, that would be 150 over 200. The joules cancel. And what would that be? 3/4? That would be 0.75 or 75%. So that would be the efficiency of the hypothetical machine where friction requires an extra 50 joules to overcome friction. Here's a little quick quiz. If there were no friction at all, a perfect ideal machine, what would the efficiency be? No friction, a perfect machine would have an efficiency of 100%. Because if you put in 150, none of that gets wasted. You get out all 150. It would be nice if that's how the world worked, but, that's just not the way of the world. Real machines have friction. Real machines have an efficiency less than 100%. Now, there's one final context we could apply this to. Here is a power plant. Perhaps this is a coal-fired power plant. You load your coal into this furnace, you heat it and burn it over a flame, and combustion gases are released. Those combustion gases are really hot. So we put pipes in their path in order to heat water. It's boiling, it turns into steam, and when it comes out of the tube here, it's moving really fast towards something called a turbine or a turbine. That turbine is kind of like a reverse, it's sort of like a reverse fan or a reverse jet engine. There are these big blades, and when it spins, it carries electricity to the homes. This is kind of a simplification, of course, but that's how power plants work. What's the input? What's the output? The input into any power plant is the fuel. It could be coal, it could be natural gas, it could be solar energy. If you're looking at, solar panels, it could be the wind energy that's being carried by the wind. Whatever serves as your fuel, that's the input. And the output is always, always, always electricity. But we measure electricity in watts. Watts, that's the power, that's a unit for power. So in addition to the equation, efficiency is output work divided by input, you could also use this equation with power. If you know your power plant generates, let's say, 10 gigawatts of energy, of power, but when you burn the fuel, it releases 15 gigawatts, right? So it's releasing a lot of energy, a lot of power, and you're creating a lot of power, but 5 gigawatts is being lost, okay? Where is it going? It's turning into heat, it's wasted, it releases here. There's, some cooling system that dumps some heat into a pond or a reservoir, but some is lost. And you could measure the efficiency. This would come to 10 over 15, that'd be 2/3, 67%. So there are two equations we can use. There's the work equation and there's the power equation.